Okay, everybody. Hello and welcome to this week's session of Webinar Wednesday e-learning session. This week's e-learning session is titled The Art of Meshing. And today we'll take a closer look at the meshing process inside SOLIDWORKS simulation. My name is Dae Kim. I'm a senior applications engineer here with Hawkridge Systems, and I'll be your presenter for today's session. So this presentation is going to be broken up into several sections. We'll cover some mesh basics to ensure everybody has a firm understanding of what a mesh is, why it's important. We'll also use this opportunity to discuss discretization error and how element size plays a critical part in creating a mesh that minimizes these discretization errors to help us get reliable results. We'll also talk about mesh creation tools, of course. Both the standard and the curvature-based mesh algorithms will be discussed. We'll also talk about different ways that we can apply mesh control inside simulation. Also, we'll discuss some of the new features in 2013, things like incremental meshing and also the very impressive render shell thickness in 3D. Also, we'll talk about mesh quality plots. A lot of users I see don't really use these mesh quality plots, and it can be very helpful when troubleshooting mesh problems. So we'll take a look at that as well. And throughout the presentation, I'll be highlighting techniques, tips, other considerations for mesh troubleshooting, as well as mesh refinement, both at the part and the assembly level. We'll take a look at using the check geometry tool, interference detection, failure diagnostics, among some other tips and tricks that we'll cover. So let's jump right into it. The mesh basics here that we want to discuss. First of all, what is a meshing? What is a mesh and why are we doing it? So meshing is more formally known as discretization. And the concept of meshing can be explained basically taking geometry and breaking it down into smaller pieces that can easily have stress or other types of calculations performed on them. So the meshing or this discretization process is relevant in both FEA as well as CFD analysis. CFD is computational fluid dynamics. And you actually will see some of these elements in plastic injection simulation as well in our SOLIDWORKS plastics tool. So in simulation for structural analysis, there's essentially 3 element types available. We have the beam element, or beam mesh, which is ideal for approximating or representing long bodies with a constant cross-section, think I-beams and pipes. Then we have a shell element, shell mesh, for thin parts, think sheet metal components or plates, gusset plates, and things like that. Then the last element here, which is our main element, is the solid tetrahedral mesh, which basically can be applied to any type of geometry. Now, the beam and the shell mesh are there for us to approximate the geometry when the solid tetrahedral mesh isn't very ideal. Let's say we have too many elements, excessive number of elements, or the geometry doesn't lend itself well to the element size. This e-learning session will focus primarily on solids, but we will discuss the shell meshing at the part level, and we'll take a look at it a little bit at the assembly level as well. So real quick, solid tetrahedral is our main element. So it is a 4-sided pyramid made of triangles, and a giraffe quality element has 4 nodes. High quality element has 10 nodes and can map curved geometry and is parabolic. We also have the shell mesh, which is triangular, both giraffe and high quality. Giraffe quality has 3 nodes. High quality has 3 additional mid-side nodes. And just to break it down for you guys as a quick review, in a finite element solution, we calculate the displacements at the nodes first. Then the resulting strain and stresses are calculated. And each node has a degrees of freedom, certain number of degrees of freedom. Solids has 3 translational degrees of freedom at each node, and shells have 6 degrees of freedom at each node, both translational and rotational, which need to be calculated. Also, you can think of a mesh as having to map the initial and also the final shape after the loading has taken place. And in areas where we expect high stress gradients, maybe smaller features, we need to resolve these areas more accurately to reliably calculate these stress results. And you may have heard the term discretization error, and we'll use this time to try and explain it and simplify that idea. So we have two-level elements available in simulation. Generally, we have the draft quality and the high quality element. First order, which is linear, and second order, which is parabolic. So if we were to use the draft quality element around a curve, for example, the hole here, you can kind of see the tessellation going around this hole. And basically, you can think of discretization error as the difference between the mesh's curvature and the real life curvature. So for example, the high quality element is parabolic and can map parabolic curves, but in the real model, a curve may not be parabolic. It could be quadratic or cubic, and therefore that little discrete difference between the actual curvature and the modeled curvature is known as a discretization error. You could think of it a lot simpler in this way. Think of measuring a curve using a straight line segment. And think of our segment here as our mesh element. So, the larger elements we use, the fewer number of elements we'll have to map this curve, and our measurement will be less accurate. The smaller these line segments that we use, the more of them that we can fit onto this curve, and we'll get a more precise measurement. But there's a trade-off. It might take us a little bit longer to count and add up all of those individual segments. So think of it like that. The finer the mesh, or the more elements that we use in our model, the greater the reliability of the results, but at a greater computational cost. We may have to just to wait several minutes or hours, depending on the size of the model and complexity, for it to run. So you could think of discretization error was analogous to measuring a curve with straight lines. So that means that there's a significant impact of element size. Element size plays a critical role in how reliable our mesh can be and our solution attained from that mesh can be. More nodes that are available for calculating the response, therefore the solution is more precise, right? So if we use smaller elements and more elements to map our model, we end up with many additional calculations that we need to do, but we can more accurately capture and resolve these complex responses. Also, if we use more elements, that means we generally are using smaller elements, so that helps to minimize our discretization error. And the practical limit where mesh size reductions don't change a result can be found in the convergence process. For those of you that are new to this term, convergence, we do have a document in our Hawkridge Systems customer portal that does cover convergence. I highly recommend that you review the document. You will probably learn a few things about convergence and some of the ways that we can calculate those values. And it's important to also note that the converged mesh for a given geometry is dependent on the load direction and the restraint, not just the shape. So the initial mesh between two parts with different loading might be the same, but in this example here, you can see that we have one load going in one direction, sort of into the page, another load going in the positive Y direction vertically. And you can see where the locations of the stress concentrations are different. Therefore, the converged mesh, or the refined mesh, is different for each problem. So it's not just dependent on the shape. It's not just dependent on, okay, there's a fillet here, let's use a small element. It also depends on, where the stress concentrations are occurring and where your areas of interest lie. So let's talk about mesh creation tools. We have two mesh creation schemes. We have the standard mesh and the curvature-based mesh. And generally speaking, we're seeing more and more curvature users go toward the curvature-based mesh. So generally speaking, in a simple model, a curvature-based mesh will create more elements than a standard mesh. Think of just meshing a simple cube, for example. If we mesh a cube with a curvature versus a standard using the same element size, the standard will create less number of elements. However, the curvature-based mesh is more robust. It's sort of an adaptive technique, and it'll allow us to mesh complex geometry with less effort and less input. Also, the curvature-based mesh really shines at the assembly level or multi-body part level. The curvature-based mesh lends itself really well to the multi-processor computing, especially in the volume filling stage of the mesh. And then we'll talk about mesh control as well. Some of you guys probably already used this before. It lets you specify a smaller element size on faces, vertices, edges, and entire components or bodies. One thing to note, curvature-based mesh does ignore mesh control at vertices, and if you do try to apply it, you will see a little message there inside the property manager. So let's talk about the standard mesh first. It activates the Voronoi-Delaunay meshing scheme. And basically what it does is it meshes the surfaces first, it meshes the faces first. Then it uses the tolerance value to knit them into a solid, and then once that has been knit, it fills the volume with these tetrahedrons, with the rest of the tetrahedrons. So we have two inputs for the standard measure, the global element size and the tolerance. And the good thing about the standard measure is that it does tend to avoid sharp triangles or triangles with high aspect ratio, and I'll illustrate that in a second. And tolerance can also be a cause for problem here, so we have to watch our tolerance. For example, if we have a gap in our model that we want to resolve, we need to make sure our tolerance is smaller than that gap. My example to the left, I have a 0.5 mil gap, and I set my tolerance to be less than that. You can visibly see that we've resolved the mesh, and there's a gap that I can see here. To the right, I set the tolerance to be greater than that gap, 0.5 millimeters. And what's happened here is it improperly merged the nodes, and so I wouldn't be able to reliably attain any sort of results with this because it's an improper representation of my model. So again, tolerance is used in two places, and if used improperly, it's possible for us to get unintentional merged nodes. So just something to watch out for, especially when you're analyzing, let's say, sheet metal parts or parts with gaps, sheet metal parts with rips, and so on. The standard mesher also has several other options. One of them is called automatic transition, and this is a nice feature to use in simple parts, but I do recommend turning this off for complicated parts and also assemblies, simply because it can create excessive number of elements, especially in regions of just simply smaller faces or smaller features. And for the most part, I like to have control over where my mesh refinement occurs. But this isn't a bad option to take a look at, in your initial mesh for a fairly coarse mesh on a fairly basic component. We also have another option here for standard mesher called automatic trials for solid. And what it lets you do is it lets you set up a number of loops here. We can set up a maximum of 10 trials. And this option here is specified in our simulation options. And basically, if our mesh fails, it will try 80% of our global size and try again. If that fails, it'll try another 80% of that size and try again. So it'll just reduce our element size by 20% each successive run. And this is a value that you can change as well. And this works pretty good for simple components, but it's something that you probably want to stay away from when you get into complex assemblies, especially if you have automatic transition on. You may end up with excessive number of elements. So now we have the curvature-based mesher. So as a summary, the curvature-based mesher creates more elements in areas of higher curvature. It tends to be more successful than the standard mesh with default mesh element sizes. And the volume meshing process of the curvature-based algorithm takes advantage of multi-core processors very well. And therefore, it generally performs much better in a multi-processor environment, particularly in assemblies. The curvature-based mesher is also interesting as well because it does a little interference check for you. If we have interfering bodies at the assembly level or at the multi-body part level, it'll automatically tell us that we have that interfering bodies and won't let us continue to mesh unless we've got a shrink fit contact or something like that applied. So our inputs for curvature-based mesher are maximum and minimum element size. And those are pretty straightforward. It'll use the maximum element size in locations where it deems necessary and the smaller element size in locations of higher curvature. And an option that drives the density of the curvature-based mesher is this minimum number of elements in a circle. And it's a value that's very commonly misunderstood. So a lot of users believe that this value here actually will place 8 elements around a physical hole in your model, but that's not actually the case. What it's actually doing is it utilizes this value that we key in, and also the minimum maximum element size. And the way that it determines the number of elements it should place on the curve is determined by an imaginary circle. So let's say we use the value of 8 here, and let's assume that our h lies in between our minimum and maximum value. And basically, we'll see that in an imaginary circle, minimum elements are set to 8, so we'd have 2 elements for this red arc. So if we increase this to 16, we would have 4 elements on this red arc, assuming that this red arc was a feature in one of our models. So if you're finding that your highly curved areas are somewhat coarse, and you could use more mesh elements there, you can increase this to get a higher mesh density. And I'll illustrate that in a following model. The next option here is the element size growth ratio. Essentially, it specifies how quickly or how fine the mesh becomes as it approaches a smaller mesh element size. If we use a ratio that's closer to 1, you'll notice that element sizes get very fine as they approach the 1 millimeter. With a ratio that's slightly higher, set to 2, you'll notice that the elements remain fairly large and coarse until we reach the location where the element is much smaller. So this, for the most part, we recommend that you leave the element size growth ratio to the default rating, unless you find a compelling reason to change them. And a lot of the times you might find reasons, especially at the assembly level, when one part interfaces or contacts another part and you're trying to get a compatible or incompatible mesh between those two. And again, because we're physically trying to map our mesh to the physical model, it's important that we interrogate our model. And geometry has a huge impact. The features on our model will control whether or not our mesh fails or succeeds. Sliver faces, short edges, small faces tend to be the most common cause of meshing problems. The mesher has to respect all the edges, and if an element size is bigger than a face there, we may have distorted element because the element itself can't fit on that face. So it's always important for us to inspect our model. Inspect it before, inspect it during, inspect it after. And the reason why this is important is that if we try to use too large elements and fit them into these tight locations, we can end up with elements that deviate from the ideal shape. So ideally, we want a triangle that's equilateral, all sides equal. But as we start getting these sliver faces, or if we place one single large element around a fillet or something like that, we could end up with what we call a high aspect ratio, or what we call a sliver element, and also this Jacobian, where an element sort of self-intersects and bends into itself. So we have to watch out for these particular issues. And there are some guidelines. There are some general guidelines when it comes to aspect ratio and Jacobian. And these are the mesh quality plots that we can use to interrogate the quality of our mesh. And basically, the aspect ratio is the ratio between the longest edge and the shortest normal. And we want to try and keep that aspect ratio value under 50 in anywhere stresses are of interest. The Jacobian doesn't have a set value. The way that the Jacobian works is that if the value is closer to 1, the better. It should not be negative. And we can check the Jacobian based on 4, 16, 29. We're placing these Jacobian points at nodes. And if you do interrogate your model for the Jacobian, you have to create a mesh with 4, then look at the Jacobian plot, then create a Jacobian plot with 16, then look at the Jacobian plot there, create another mesh with 29, and then look at the Jacobian again and compare the values. So it's an iterative process with the Jacobian. And the way that we resolve these issues is by using mesh control and using smaller elements in locations where we need it. Right? So mesh control lets us apply mesh control to vertices, edges, faces, bodies, and components. We still have the element size growth ratio down below. Again, I would recommend leaving that default unless you find a reason to change that. But in general, the local mesh control on smaller faces will improve mesh success. And there's also sort of a general rule of thumb that you necessarily don't have to adhere to at the part level, but it does come into play, especially at the assembly level. But generally, try not to transition between mesh sizes varying more than a half to a third of the global element size. And you've also probably noticed that whenever we hit reset, it sets the mesh density to a certain default element size. And that default element size is calculated internally by the software. It takes into account the volume, the smallest features, the smallest dimensions, as well as the element type we're using, standard versus curvature or versus shell elements and so on. So once we have that default element size, then we can pick and choose to see whether or not if we want to start off with the default element size or adjust the default element size and start off with something other than that value. So with the mesh creation tool, there are a few recommendations. Basically, you can use the mesh creation tool to place a refined mesh strategically in your model in areas of interest or areas of high stress gradients. And again, try to adhere to the 1/3, 1/2 rule for the global element size for surrounding surfaces. And again, you can recommend keeping the ratio to default unless you find another reason to change them. I always recommend that you try a couple of meshes. It is an iterative process. Meshing complicated models is a very iterative process, and we will find success in trying out different values and different techniques. There's also another interesting way that we can apply mesh control, and that's using split lines to control the node placement. And I'll illustrate that here as well. All right, so let's take a look at our model, at our first model. And this gem was provided by our product manager, and this model has been purposely created to be a pain to mesh. You'll notice here we have areas of very large faces. We also have areas of very small faces. Notice that this fillet isn't a full round fillet. There's actually a small face on the top there. We have a lot of these small holes, edges. These holes are also drilled, fairly close to the edge, fairly close to each other. And I expect there to be some issues in those locations. And so we want to interrogate our model, right? So we want to check the geometry, visually inspect for unnecessary features, short edges, sliver faces. If we can simplify either manually or using the simplify tool. And we'll also use the check geometry tool to look at closer inspect our part here. And also at the assembly level, we'll talk about that in a second, but check interferences as part of the assembly. Okay, so let's go ahead and check our geometry. Well, there's nothing that I want to suppress here because this is meant to be a challenge, so I won't simplify the model, but I will leverage our check tool. So I can go to the tools pull-down menu or the evaluate tab, and there's a command here called check. And this is called check geometry. This is definitely a critical step for those of you that run models that have been imported outside of SolidWorks. So if you're bringing in step files, IGES files, and other converted models, it is a good idea to check this out. You can do a stringent solid and surface check, which can help you find if you have any invalid edges or faces. And also you can leverage this tool to look for short edges, which is pretty cool. For example, find me edges that are shorter than 1 millimeter. And we have a pretty large list. 1129. Okay, so let's go something shorter. Let's do 0.1 millimeter. And it's found 4 edges, and it does throw a little arrow on there for me, which is pretty nice. Now, this doesn't necessarily mean I have to use an element size of 0.1. It just helps me look at locations where mesh problems may occur. Right? And what's going on here, if I flip inside, is we have some holes here, another little sliver edge here. So it helps me find these odd locations where I can have some issues occur. This tool is also handy if you want to leverage something like the minimum radius curvature. And also these options for maximum edge gap and maximum vertex gap can be helpful for you to find potential locations where issues may occur. So I'm going to start off with a curvature-based mesh. I mentioned the curvature-based mesh tends to have more success with the default element size. So I'll click reset here. We have our maximum minimum element size, minimum elements in a circle set to 8, and I'll use the default element size growth ratio. And we'll go ahead and apply a mesh to this complex part and see how the curvature-based mesh fares. Right. So there's our mesh. It was actually able to complete with my default element size. I didn't really have to do much to get this to complete. I was able to just go ahead and apply the default 7.27, 1.45 millimeter element sizes to that. We could also interrogate our mesh. If you right-click on the mesh folder, you can select details, and that will give you some information about our mesh. For example, how long it took to mesh, how many elements we have, how many nodes we have, and that's indicative of how large the problem will be and how long it might take to solve. And also we have little checks for aspect ratio. Maximum aspect ratio, 866. Percentage of elements with aspect ratio less than 3. 71% of my elements have an aspect ratio less than 3, which is good. Then percentage of elements with aspect ratio greater than 10, I have about less than 1%. But that maximum aspect ratio of 866 is pretty high. So that is alarming. I'm going to create a mesh plot to take a look at that. So if I right-click on the mesh, I can create a mesh plot. It's found underneath the Apply Mesh control. And this here, the actual mesh, is a mesh plot. So if you wanted to create this, it's essentially looking at the mesh that we've loaded to view. Now I'm going to create another plot here for the aspect ratio. And if we look in here, 866 is pretty high, and if we zoom in, we can kind of see where we have these heavily slivered elements. 866 is very high. We do want to keep it, try to keep it at double digits if possible. If my stresses weren't of interest here, maybe I'd leave that, but still it's a little alarming to have an aspect ratio that high. And as a slide indicated previously, if we have an element that has a high aspect ratio that deviates from the ideal shape, the element itself can calculate a little bit more stiff than it should. So in an effort to keep our results as reliable as possible, we want to try and resolve this issue. And we can resolve this issue in a couple of different ways. One of them is mesh control. The other is using a smaller element size. All right, so I can go ahead and start a new mesh. I'll slide the slider over to find this time and see how this fares. Now, just because it completes in the default element size doesn't mean it's going to be successful in the define element size. So this is applying a smaller mesh element now around those regions. And we're going to have a denser mesh. We're going to have more elements that are mapping this component. And so you can see here visually that the density has increased. I can look at the details of our mesh again and see that now I have 92% of my elements with the aspect ratio less than 3. My maximum aspect ratio has dropped from nearly 1,000 to 260. And it took 35 seconds to complete our mesh. Another thing I noticed is that, you might be tempted to start off with a draft quality mesh, but there's really no difference in runtime or the time it takes to mesh between a draft quality and a high quality. What you gain from the draft quality is actually when you hit run and calculate the displacements and the stresses. All right, so let's take a look at our aspect ratio. And it's still somewhat in the same region. We have some elements of high aspect ratio around this tiny hole here. So then we can go ahead and take another approach. If we'd like, we could go ahead and now this time apply mesh control. And I'll go ahead and apply mesh control to that edge. And we could do something like 1 millimeter. Once we apply mesh control, we want to create the mesh over again. So you'll notice that, again, for something like this, even when my initial default mesh completed, it's still an iterative process to find the refinements and make the improvements to my mesh. Okay. So now I should see an improvement around that hole, since it should be using those smaller 1 millimeter element sizes around that region. So again, I could leverage mesh details or the aspect ratio plot. Now my aspect ratio is down from 260 to 85. It's much improved. And it looks like the aspect ratio is somewhere inside the model. Oh, there it is. Pretty high sliver face there. Another interesting trick that you can use here is that, there's no easy way for us to interrogate the mesh through the volume, right? We can see here, if we show the mesh, we can see the mesh on the faces pretty easily, but there's no easy way to interrogate what's going on in the volume. So one of the ways you can get around this is by using this aspect ratio plot, but it's still not a perfect view. But what you can do is then do something like section clipping. And we can pick the appropriate plane here. Section clipping. And let's go ahead and switch my view over. So right now it's tough to see because of the way that my color chart has been set. So let's go ahead and set my color chart so that it's a bit easier to see these other lower aspect ratio triangles. Go something like 5 or 10. And then using section clipping, I have a way of interrogating my model through the volume. Oh, I get the plane back to the right spot here. So once we look at the aspect ratio, then we could take a look at the Jacobian as well. And the Jacobian is available for high quality elements only, because high quality elements are the ones that can map curve geometry and bend and skew. And so it looks like the highest Jacobian is found on this small filleted face. And a value of 29 isn't alarming, but it's not too good as well. But if I wasn't concerned with the stress results in this location, then I might be fine with it. Otherwise, I could apply mesh control at that location. Now, if we take a look at it using a standard mesh, the standard mesh is going to be sort of a different story. The standard mesh is going to take a lot more work up front to get our initial mesh to complete. So in this one, I actually started off with a large element size to illustrate that if we start off with a large element size in standard mesh, it can leave us with a lot of mesh control requirements. So if we start off with a larger standard global mesh, it might be fine for these large areas of our model. But when it comes to these small faces, we're going to have more of these locations where that global element size can't fit. So I tried to mesh this with that large element size, and it failed. And when it fails, I can right-click the mesh and select Failure Diagnostics. And it opens up this window here. And I just wanted to use this as a comparison. When I tried this overly large element size, I've got 3 faces that failed to mesh and hundreds of edges, about 600 edges that also have failed to mesh. And it's kind of daunting to try and apply control to all of those. So the way that you can interpret this is, okay, I may have to try, starting off with a smaller global element size. If you start off with a smaller global element size and a standard mesh, you probably have an easier time resolving small features that exist in your model, but you'll end up paying for it when you hit run, because you'll end up with excessive mesh elements in locations where you don't need it, like these large faces. So let's compare that to this mesh here. I ran that with a slightly smaller element size. I said, okay, 7 is a little bit too large. So now let's compare the result here. And now we can see that with the smaller element size, we only have one face that has failed, and still a rather large number of edges that have failed as well. So you can interpret this two ways. You can say, okay, if I may need to lower my global element size some more, or if you are feeling like your global element size is good enough, then you can try and apply some mesh control to get through these regions. For me, though, this is a lot of mesh control to apply, so I would likely try a smaller element size to begin with. So let's go ahead and start a new study just to mesh. And I'll start off with the standard mesher. And I'll start off with our global element size. So the standard mesher, recall, it meshes the faces first, and then it tries to knit those faces using our tolerance. And then it will attempt to fill the volume with the solid tetrahedrons after it's completed meshing each of the individual faces. So when that fails, I can leverage the diagnostics tool. And what I really like about this tool is that it sort of acts as a guide. You can apply mesh control, or you can check the geometry. We've already checked the geometry, so I'm going to apply mesh control here. And I can actually select these 10 edges directly from this little window. If I select the edge folder, I actually grab all 10 of those edges. I'm going to take a slightly aggressive approach and set an element size of 1 millimeter to that mesh control. And when we run this, we can then try to interrogate the model and see where if that mesh control was enough, or if maybe I need to toggle my global element size a little bit more. I'm still going with a fairly large global element size, about 3.6 millimeters. So one of the things that we'll see here is that it's failed again, and we've got several other edges that need mesh control. But when we take a closer inspection, we actually are those same edges. Those 3 edges are part of the 10 edges that I selected initially. And generally, what you should see when you apply mesh control to the same edges, you'll see a warning that says, hey, there's a mesh control already applied to this edge. The smallest mesh control will be applied. But I could interpret this a couple of different ways. For example, I could interpret it as a way of saying, okay, I do need a smaller element size on those 3 edges particularly, or the global element size is having a hard time transitioning to these smaller element sizes on these edges. So I'll go ahead and be a little bit more aggressive and use a smaller global element size on my standard mesh. And this is to try and aid to make the transition between the large 2 millimeter element size to the 1 millimeter element size a little bit easier for the mesher. Okay, so once this is completed meshing, we'll be able to see whether or not we need to apply additional controls. And we'll also be able to interrogate, how long it took to run, how many elements, total nodes we have. And it looks like that slightly aggressive approach succeeded. We take a look here, we can see my mesh is completed. And just interrogating it real quick and comparing it to our curvature-based mesh, notice that our maximum aspect ratio is less than 100. And again, that's partly due to the fact that the standard mesher does a better job of avoiding sliver elements, but also we used a fairly small global element size to begin with, therefore our aspect ratio is aided. Took a little bit longer to actually create the mesh, almost a minute, and we've got about 100,000 total elements. So we could see here, with the standard mesher, especially, that it is still a rather iterative process where we do a lot of trial and error to see what works and what doesn't. You want to try and throw, several different element sizes at it to see what sticks. Now, if you're still having issues, then there is a more aggressive approach that you can take, and that approach involves actually physically cutting your model, and it allows you to take a piecewise approach to the problem. So you cut your model into a third, half, or a quarter, and then you mesh from there. You mesh your model into the quarter of the model or half the model, and you take a piecewise approach to see what element sizes work, what doesn't. And when you find a problematic location, you'll be more easily able to resolve that issue at that location, because you'll have also a smaller model to mesh, so it'll take less time to actually complete the mesh, and so on. So that's an aggressive piecewise approach that you can take at the part level, is physically cut the part into a half or a quarter to run along with that. Also, a quick example on split lines to control node placement. So we have a quick little model here. And when we're using, let's say, a curvature-based measure, one of the things that I've seen here is that here's the circular edge, and you can see the mesh around the circular edge. It's not very uniform. You can see how the elements sort of skew out of place. And sometimes you might want to resolve, cylindrical geometry very cleanly, possibly for symmetry. Maybe you want a symmetric mesh in your model. So what you can do is leverage split lines. And split lines essentially is helpful not just for creating regions where you can define loads and fixtures, but where that edge lies by the split line is where the nodes will be placed. So you can look at this example here. You see that the nodes have been placed along this edge, and we have a much more uniform mesh. By go ahead and actually don't want to. Okay, so let's go ahead and create our mesh here. I think this one's a different mesh. Let's just go ahead and create a standard mesh. There we go. So you can see now we have two elements before it gets to that edge, and it's much more uniform around that cylinder. Also, the benefit of this is it actually places the nodes at those locations. So when I probe on selected entities, I could probe the edge and probe nice plots along certain edges. So this split line technique is really helpful when you're trying to get a symmetric mesh, or when you're trying to get a better mesh around a small component or small feature. So again, visual inspection is key. Simplify the model, use the check tool where applicable. Now let's talk about shell meshing. Real quick, shell elements are a more efficient way to model thin-walled structures, but we have to understand their approximations to the real geometry. They're useful for interrogating the overall behavior of the system rather than detailed stress results in the shell thickness or between the shell and other parts. And the way that you can try and figure out if the shell mesh is an ideal assumption is you can interrogate the model by trying to create a mid-surface version of that model. And if it looks fairly similar, then it's likely a valid solution. You can also go by the thickness. If the thickness dimension is much smaller than the smallest feature size, and shells may be a consideration. And there's two ways to essentially create a shell mesh. Model a mid-surface representation of the solid, or define the shell by selected faces. And question about thin and thick shells. Basically, thin shells ignore shear deformation, and thick shells assume a constant distribution of shear deformation. If you're not sure, I recommend going with thick first. You always do want to run some comparisons to make sure that your assumptions are valid. And sometimes it's not very handy to create a mid-surface model. Maybe you just have the outer face or the inner face. So you can create a shell using the outer face of your solid model or the inner face of your solid model. And in an effort to try and get the shell to lie at the midplane, we can use a shell offset here. And the shell offset is has always been sort of difficult to verify. We've really had to rely on our expertise and past experience to go by how this offset works. But the way that this top surface, bottom surface option works is it's highly dependent on the shell alignment of the actual mesh. And now in 2013, we can use Render 3D to help us with that. So real quick, when I specify the top surface, that means that the thickness is created in the direction normal to the bottom face. So for example, here, since my bottom face is below, it's going normal to that bottom face. It goes down in the negative y direction. If my bottom face is above, it goes again normal to the bottom face, and it goes up in the positive y direction. Opposite of that, if I select the bottom surface option, it assumes that the thickness is going toward the top face of the model. So it's really important for us to make sure we have these directions correct. So let's take a look at a model here. There's two approaches I want to illustrate. I've actually got a solid model and also a simple surface model that I've modeled for a mid-surface representation. And we actually do have a mid-surface feature. You can actually leverage that inside SolidWorks to create a mid-surface. So this works for fairly simple components. It won't work for all complex geometry. But for a component like this, it's not too difficult to create a mid-surface. Right? And I've also placed the top plane so we can see where the mid-surface actually does lie. I'm going to hide the solid. And when we jump into the surface mesher here, when I edit the definition of my surface body, I could key in the thickness that it represents and the offset value. Because I'm using the actual mid-surface here, I'm going to leave my offset to 0, which means it's going to apply this thickness in both directions. I can create the mesh, and I can now render that mesh thickness. Previously, it used to just be a flat surface, right? And we have the top face, the bottom face. The bottom face is orange, top face is gray. Now I can render the thickness in 3D and really inspect my model with some confidence and have some confidence in my shell definition. You can see visually that the thickness being represented is proper. And we can also see the effects when we make the wrong selection. If I selected this to be the top surface, it extrudes it normal to the bottom. And so now it's sitting on the top plane instead of passing right in between it. So it's really important that that we utilize the correct offset. And this really comes into play here at the part level with solid models here. So what I'll do here is define shell by selected faces. Here I have a solid plate. I'll just go ahead and right-click that, define shell by selected faces. I'll select the top face of my model, 5 millimeters, and I'll try and keep things intuitive. So since I selected the top face of my model, I'll select the top surface option. I can create our mesh. And in the past, this is what we'd see, just that surface that we select being meshed. But I can render shell thickness in 3D now and see which way that virtual thickness is actually going. And it's actually now extruding away from my midplane. Again, because I selected the top surface option and my bottom surface is facing the top direction, it's going the wrong way. So I have two options. I can switch that to the bottom surface, but that means if I want to look at the results on the top face, I would have to look at the bottom shell results. So to keep things intuitive, I can just select my meshed face there, right-click on my mesh folder, and flip elements. When I flip the shell elements, now it extrudes correctly downward from that top face, and we can get a correct representation of our model. And this is also handy when we render the shell thickness for our results here. I can also probe values. And depending on our results, we'll see that the bottom portion of my model is in tension and the top part of my model is in compression while this plate is in bending. So it also allows us to interrogate top and bottom results at the same time. Also, when it comes to meshing assemblies and multi-body parts, we all have an option to look out for. It's called the compatible versus the incompatible mesh. You can alter it in the global component contacts or global contacts, and you can also specify to remesh the failed part with an incompatible mesh. And basically what it does here is an incompatible mesh, it tries to merge the nodes between two bodies, and it'll allow for an easier, a more accurate bonded contact that can be calculated much easier. Otherwise, we end up with an incompatible mesh where the nodes aren't merged, and this will require additional constraint equations to be run. So it may take a little bit longer to run the incompatible mesh, but it is much easier to get these incompatible meshes to actually mesh the model. So the reason being is that the compatible mesh can cause problems, especially when it comes to the position of components. If we leave sliver faces in between two bodies, it can have difficulty creating a mesh there. And also, if we have a very, very small part, think of a washer coming into a very large, prismatic machine fixture, that change in geometry can also have an impact on how easily things can mesh and fail. So, when we look at the assembly level, I've got a knuckle component here from a boom arm. And what we'll do is take a look at the main bracket in this assembly. So here we'll take a look at this knuckle kit that we have. And you'll notice here that, again, we want to visually inspect our model and see that I got some small features on this washer, probably insignificant. Not too interested in this grease fitting. So what I'll do is, I've created a simplified version of the model, and that's pretty easy to do. You can just come in here, copy and paste, and suppress all of these additional cuts and unnecessary features. Possibly also use delete face command as well. And so I've got a for analysis configuration that's been simplified, and another component's been put in to define the load. And this one's pretty interesting here, just to mesh. So let's start off with a mesh. I'll start off with the default element size. And this model does a pretty good job of showing how that compatibility can cause issues. So look, all right, my default mesh worked no problem. So let's try another one. My default worked, maybe my fine will work. So let's try to throw our fine mesh element size at it. And surprisingly, it failed. And the main reason for this is because of the interface between that small washer and that knuckle. So I have a couple of different options here. If you show the mesh, you'll be able to visually see the components that failed to mesh are not in the mesh plot. So my knuckle and one of my washers has failed to mesh. So I have a couple of options. One of them is incremental meshing. Here I could, right-click on both of these and create a mesh and apply a mesh control to this. But this incremental meshing, I should note, only creates a curvature-based mesh and an incompatible mesh. So when I hit yes, it meshes only the failed parts, but it's meshed them with a curvature-based mesher and set it as an incompatible mesh. So that's one quick way of resolving this issue. The other way of resolving this issue is to, again, trial and error, through the trial and error process, search for a set of element sizes that work. So the 16 and 3 didn't work. Maybe we try a smaller variation of that, right? So I can try something like 10 to 2 and see how that works. I could also try and play around with the element ratio. But from my experience, I found that setting the element ratio to lower doesn't really aid in trying to make a compatible mesh between components. So that was able to complete without issue. You also have another option inside the mesher, this option here to remesh failed parts with incompatible mesh. That's something that you can toggle on just sort of as a fail-safe. But again, you'll have to understand that it will create an incompatible mesh between the parts that failed to mesh. So, if we take a look at this at the using the standard mesher as well. It does a pretty good job with the default element size. But in a similar fashion as the curvature base, when I try a smaller element size, there are ranges that work and ranges that don't. And a lot of it does have to do with the whole compatible, incompatible issue. So it's a matter of, how much work you want to put up front to try and get this to mesh with the compatible versus incompatible. There is a trade-off, right? So if I say, what, I'm not going to spend, an hour or 2 hours to troubleshoot this mesh, I'm just going to go ahead with the incompatible mesh. Then you do trade that off with a little bit longer runtime, right? So just how much longer is that? I've got a dense standard mesh and an incompatible dense standard mesh both run. And when we take a look at the messages here, my dense standard mesh actually ran in 30 seconds and had close to 1 million degrees of freedom. But the incompatible version of that, because it requires additional constraint equations, it took about 5 minutes to run at about 900,000 degrees of freedom. So that can sort of, get an idea or quantify where the trade-off lies. But it is some level of trade-off as less input required, less effort required at the beginning, and a little bit more runtime to deal with at the end. And another example here is that the mesh that I created here using the fine failed for the solids. So another approach that we can take is representing components like these washers that are really small compared to the other adjacent components to represent it a bit more efficiently. For example, when we look at this standard mesh, the idea is that we want to make sure we capture bending properly. And in order to capture the bending and various other phenomena properly, we need at least 2 elements across the thickness of our washer. And so that's what I've done here. And that's how we end up with so many elements, like about 1 million degrees of freedom just for a couple of those washers. So in this example, what I did was use define shell by selected faces to create this mesh. And the shell mesh, you can see, again, using the rendered shell thickness, we can make sure that the washer does contact properly and isn't being extruded into my knuckle. And when I compare these results to a solid mesh, they're within 5%. So it's very reliable. And then this was actually able to mesh using the slider all the way over to fine because there wasn't that issue with the compatible incompatible mesh between the washer and the knuckle. And also, once we've got a result run, now you want to think about where do you want to apply mesh control. One of the things you could do is look at the error involved and create a stress plot for energy norm error. And essentially, it's the difference between the element stresses and the nodal stresses. When I probe these values in areas where my high stress lie, you can see that I've got error up to 26% in that region. So 26%, 24%, 10, 12%. So I can try to improve that by applying some mesh control in these regions where I have that stress concentration. Right, so I can apply mesh control to this edge, try a smaller element size, and we can mesh and run this. And we can look at the error, probe it again. And now they're down a bit lower to the 6s and 7s, but there's still areas where there's slightly higher error, so I can go ahead and further refine my mesh at those locations. So in this example, the model wasn't too tough to mesh, but you can also take a piecewise approach to a model like this when you're having a very difficult time. The idea here is you can come in and suppress different components, mesh it, then bring in the component that has failed. And when the mesh fails at that component, you'll notice you'll be able to identify where that interface or where that problem location lies. So just sort of a summary of the troubleshooting tips. Again, inspect your model, perform a visual scan, and try a mesh with the default element size or slightly adjusted element sizes first. If it fails, use the diagnostics tools, the check geometry tools, and take an iterative approach. If all else fails, then cut the model into a half, a quarter, and take a piecewise approach to the problem. And for assemblies, similarly, you can perform a visual scan for parts. You can also run an interference detection to ensure the contacts and your component contacts are being applied properly. If all else fails, you can try, the incompatible mesh and just deal with a slightly longer runtime. And also take that with the piecewise approach. You can combine that with the piecewise approach to the problem and mesh individual parts or suppress components of the assembly and mesh pieces of the assembly at the same time. And just a word of caution here about contacts. The contact area should be greater than 0. So you don't want like the point of a cylinder contacting a face or a line contact between a circle tangent to a planar face. You want to try and avoid those things.